See, from today onwards, we are going to start this, the fastest revision of the mains as well as NEET schedule for organic, physical, and inorganic. So, listen. The first question is, which of the following gives Hydroform test? See, children, see the concept I'll tell you here. That's nothing but that should have what you call as CH3 CHOH group, or it's going to have what you call as here CH3 C double bond O group, CH3 C double bond. So that means it should contain alpha methyl group. That's okay, children. And next, this is the first point to give what you call as here hydroform test. The reagent is, it's going to be NaOH, I2, or it's what's called here Na2CO3, aqueous Na2CO3 and I2 also. And these two can produce our commonest attacking reagent NaOI. NaO minus I plus. I plus, that's going to replace all the alpha hydrogens and gives rise to iodoform. So that's the main condition which is going to be discussed here. It should have CH3CHO group, or it should have CH3C double bond O group. That means it should contain alpha methyl. So I'm finishing all the concept here, children. For example, let's see this. We are doing with this. What we are going to do this means, I'll take acetic acid. No, I'm taking here acetic acid. See, is it response, Baba, here? Having alpha methyl group? No, because it's resonance stabilized. It's going to be stabilized by resonance. Hence, it's reluctant to release alpha hydrogens. It's reluctant to release alpha hydrogens. That's one. And one more example also. I'd like to go through this and whatever is called here like acetamide. Let us take acetamide also. This is also doesn't respond for this because it undergoes tautomerization. Hence, the liberation of what do you call as your alpha, the replacement of alpha hydrogens is going to be very, very difficult. So this is the first question. The option is going to be 4. Which of the following would give iodoform test? CH3, CHOH, CH2, CH3. See, in all these cases, you doesn't find this alpha methyl group, right, children? This is secondary alcohol test here. Exceptions, acetic acid and this. And here I am going to write one more thing. Let me take this, just I will make down acetophenone. When you are taking acetophenone, children, that is going to be treated with iodoform NaOI. Right, I'm taking direct reagent. The mechanism part is given in my notes. Everything you can see. I plus NaO minus will attack this. And this all is replaced here and gives rise to CHI3, and that's going to give us sodium benzoate. So with one example also I have done, one of the precious example, children. So this is the first question, Baba, here. Let me do with what do you call as your second question. Aspirin is example of hydroxy ester, ketoester, aromatic acid ester, and phenolic compound. See here, it's going to be an aromatic acid ester. How it is going to be aromatic acid ester? Let us see, children, here. See, when you are taken this salicylic acid, is treated with acetic anhydride in presence of concentrated H2SO4. In presence of what you call as here concentrated H2SO4, that's you are getting acetyl salicylic acid. That's you are getting here acetyl salicylic acid. That's also we are going to see here. Let me do this. This is salicylic acid. Whenever you have taken this salicylic acid, is going to be treated with what do you call as here acetic anhydride. That's the compound acetic anhydride in presence of concentrated H2SO4. That's going to give us acetyl salicylic acid. So COCH3. This is what's called here aspirin, children. And this aspirin, generally, it cannot be swallowed directly. It's always possible followed by the what do you call as here Zinatag, Gelisul MPS, like that Rantadine. Why? Because it's going to cause ulcers when you have taken swallowed this with empty stomach because it affects the intestinal tract, causes ulcers. That's why it's always taken what do you call as followed by the Gelisul MPS like Rantadine and that like tablets here. That's going to be the one of the most important aspect. It is aromatic, what do you call as here acid ester. That's clear. Second question is also finished, Nana here. And coming to that, that's third question I am doing with this. When I am going for third question, an unknown compound dissolves in H2SO4 but does not decolorize bromine water and does not react with sodium. Which of the following classes of molecule will behave in this manner? Simple, children. Ether. That's everybody can answer. Why, sir, it is going to be ether? Let us see. Alkene, unsaturated, decolorizes the bromine. Reddish brown color of bromine is decolorized in presence of bromine and water. And next, alcohol that reacts with what do you call as here sodium. It's going to give us sodium alkoxide. Phenol that also gives rise to tribromophenol. You are going to get tribromophenol. Suppose that tribromophenol also decolorizes bromine water, but it is aromatically stable. That's why it's what do you known as here never what do you call as dissociate the pi bonds here. That's why the ultimate one is going to be the unknown compound. What might be the unknown compound? That's nothing but what's called here diethyl ether. We will take an example, children. When you have taken the diethyl ether as example here, let us take the diethyl ether as example. And that's going to be dissolved in H2SO4. That's going to give us ethyl oxonium hydrogen sulfate. That's going to give us ethyl oxonium hydrogen sulfate. Ethyl oxonium hydrogen sulfate. Ethyl oxonium hydrogen sulfate. That's what we are going to see here. Now, it's what you know as. This is going to be dissolved here and also gives a salt. Diethyl oxonium hydrogen sulfate is going to be the compound. Let's move to the fourth question, Baba, here. Just be active, children. Let us do this question also. It's very simple. The reaction of what you call as here C6H5OH, that is phenol with chloroform in presence of NaOH at 340 Kelvin temperature. That's going to be followed by acidification to form salicylaldehyde. So that's called Reamer-Tiemann reaction. That is going to be Reamer-Tiemann formylation. So in this, what are the possible questions we will see here? What might be the possible questions, Baba, here? The chloroform reacts with KOH in the first step and it liberates what's called here dichlorocarbene. That's going to liberate dichlorocarbene CHCl3, and this is what's called here KOH. And next one is going to be, it's giving us what do you call as this? It's CCl3 minus, that's ultimately produces CCl3 minus. Finally, it gives dichlorocarbene. This is the real attacking species here. That's clear, children. And with respect to this, this is called Reamer-Tiemann formylation reaction. One step I am doing. That's called RT formylation. The ortho compound is going to be more stable. Orthosalicylaldehyde is going to be more stable. Why? Because what do you call as here? One more important thing. Let us see here what's that means. This is the phenol. Let me take the phenol. And that phenol is going to be react with this dichlorocarbon. And it gives rise to an intermediate. That's very, very important objective. Don't mug up all the things here. That's very simple thing which we have to do. Phenoxydichloromethane is the intermediate. Phenoxydichloromethane is intermediate. So this mechanism part I have given in my notes. Simple objectives, what the way to remember this. It's called Reamer-Teamer formylation. The intermediate is going to be known as here Reamer-Teamer, and this is formylation reaction here. Yes, this is what here next is going to be. Let us see this. It's nothing but whenever we have seen the part of this is what phenol. That's in presence of what you call as carbon tetrachloride and chloro, KOH. This is called Reamer-Teamer carboxylation reaction. That's nothing but known as here Reamer-Teamer carboxylation reaction. That gives rise to what do you call as here salicylic acid. Both are going to be stable. Salicylaldehyde, that is also orthosalicylaldehyde, is major product and stable also due to intramolecular hydrogen bonding. It is also stable due to intramolecular hydrogen bonding. That's what you call as here intramolecular hydrogen bonding. That gives rise to phenoxydichloromethane. And this is called what you call as here salicylic acid is going to be the product. This is Reamer-Teamer carboxylation. This is going to be Reamer-Teamer formylation. And the two more questions also we have done here. The attacking species is dichlorocarbon here. This is going to be here, the attacking one is going to be CCl3. That's attacking one and gives rise to the Reamer-Teamer carboxylation reaction. Now, children, that's what we are doing with fifth question. An alcohol, what do you call as here? C5H11OH on dehydration gives an alkene, which on oxidation gives mixture of ketone and an acid. 5 carbons are there. You are given with 5 carbons, right? The 5 carbons on oxidation gives rise to alkene. Alkene gives rise to what do you call as here ketone and acid. Let us see. That's also we will see here, children. What's going to be happen this? Let us do this also. First of all, you are getting ketone as well as acid. Ketone. The ketone is going to be minimum 3-membered one. So that's why that's what we are going to see with respect to this. The ketone is nothing but 3-membered one. So let us write first of all ketone here. What's called here? Out of, let us write ketone. Out of this 5 carbons alcohol and remaining 2 are there. One is going to be acid. They have given the hint. We are starting the question from the hint. Let's take this. Eliminate all these things, right? And combine these are all. What are you going to get, children? That's what's called here 1, 2, 3, 4, 5. This is called 1, 2, 3, 4, 5. This is 5-membered compound. This is an alkene. Let us see this. What they have done. This is on oxidation gives mixture of acids. That's simple, children. It's what do you call as here? An oxidation of this one gives what do you call acid and aldehyde, and aldehyde is going to be further oxidizes. That gives rise to ketone. and next one is going to be aldehyde that further oxidized as what's called here acetic acid. This is the way to find out the answer here, and this mechanism is known. In order to get this, what might be the alkene here, whether it is first one or second one, what's going to be happening with respect to this means the alkene is nothing but this, what's called here 1, 2, 3, 4. 2-methyl butadiene. 2-methyl butadiene is going to be the alkene, and the alcohol is which alcohol? This upon dehydration loses water molecule and gives, this is going to be loses water molecule here. This first compound loses water molecule, and that's going to give us what do you call as here hydrogen. This is H, and this is CH plus, and going to be methyl group. CH plus is there. So what's the stable carbocation, children, here? That's the possible stable carbocation is going to be. This is going to be shifted here. It's CH3, no? This is CH3, this is CH3. This is going to be shifted, and you are getting this alkene. This is the alkene which we are going to get here. So this alkene upon oxidation gives rise to acetone as well as acetic acid. This is the simple reaction. Oxidation of what you call as ketones is going to be very, very difficult, children. So that's what we have seen. Hence, the option is going to be this secondary alcohol. That's one of the most important one. And suppose, sir, secondary alcohol means here also you are getting secondary alcohol. C5H11OH is concerned. You are getting here C5H11OH. See, but see this 6, 3, 9 to what do you call as here 11, 12. Everything formula is same in all these cases. But in which case we are going to get the ketone is very much important. In this case, why? Because where there is isopropyl group, that's going to be converted as in the form of acetone. That's going to be converted in the form of acetone. That's why the most important objective is this. It's the possible answer for this. First of all, this is, we are combining this one and this one. They told it is ketone. The least numbered ketone is acetone, no? Acetone plus carboxylic acid, overall it should contain 5 carbons only. There should not be any degradation of number of carbon atoms. Let us overlap on this double bond and OH is eliminated. You are getting an alkene is this 2-methyl butadiene that upon oxidation gives acetone, acetaldehyde. Whenever it gives what do you call as here acetaldehyde, this acetaldehyde that's going to give us acetic acid, further oxidation. Clear? Oxidation of ketone is very, very difficult over here. And that's one. Let's move to the next question. Which of the following does not react with periodic acid? See here, it's such a beautiful question, children. It's a very, very important question also. You come across in the biomolecules in carbohydrates. That's an elucidation of what you call as glucose structure. See, what's the role of periodic acid? Because the mechanism, it's not possible now because I'm doing a rapid revision. Periodic acid, this is the formula of periodic acid. Generally, it's not exact formula as you feel, but it's in the inorganic part I'll discuss with you. So which of the following does not react with periodic acid? Why? Because the essential condition for this is going to be, what's the essential condition for this? First of all, we will go through this. The possible essential conditions are going to be, that's nothing but we are going to do with this. See, there should be what do you call as here, it should, the compound must be vicinal diol. The compound should be vicinal diol. The essential condition is that the compound must be vicinal diol. Essential condition is that vicinal diol. it should contain what do you call as a continuous hydroxyl group and 1 point, and it should contain what do you call as here alpha hydroxycarbonyl compounds. Alpha hydroxycarbonyl compounds. Very simple trick, I'll tell you children here. Whenever you are doing with this, no, whenever you are doing with this, and this is what we have to see with respect to this part is concerned. And here it's nothing but alpha hydroxycarbonyl molecules or compounds will give this reaction, undergoes oxidation with periodic acid. So this bond will break down, and also it break down. This carbon is broken with what do you call as here one covalent bond, CH2OH and OH, right? Then it eliminates the water, and then it is going to give us formaldehyde, and then it eliminates to give us formaldehyde. Now, whenever it is going to be alpha hydroxycarbonyl compound, and it's what's called here alpha hydroxycarbonyl compound. That's what we are going to see. So this is like this formaldehyde. Here two bonds are broken. Let us show me this mechanism. We can discuss, but it's time-taking process. It's quite unstable. 3-hydroxy group, diols, triols are quite unstable. Two bonds are broken, two OH groups are added, minus H2O. That's going to give us formic acid. Like that, B will give you. That's nothing but what do you call as 2 moles of formaldehyde. See the logic you can apply, and 1 mole of formic acid. See, also it gives Baba here. It's nothing but that's going to produce here. See, first one, this carbon produce formaldehyde, 2 moles of formaldehyde. And that's going to give us 2 moles of formaldehyde. And then what it is giving here, this terminals are giving us 2 moles of formaldehyde and 1 mole of formic acid. What's going to be given? The D. See, it's not a vicinal diol. In between this CH2 group is there. So that's not possible here. That's why it won't oxidize by HiO4. This is the concept here. Keep in your mind, children, essential condition is that vicinal diols and what do you call as here alpha hydroxycarbonyl compounds will respond for it. That's clear, Baba, here. And over, 6th question is over. Let me do for 7th question. Which of the following alcohols undergo dehydration fast? Dehydration. I'll write down very simple sentence here. Rate of dehydration, that's called rate of dehydration, is directly proportional to stability of carbocation. Stability of carbocation. That's going to be what do you call as here stability of carbocation here. So this is what we are going to see here, stability of carbocation. Now, whenever we are seeing the stability of carbocation, let's verify. This is having only plus I effect, a compound, because lengthy chain, stronger plus I effect is there. That's what's called 1, 2, 3, 4, 5 carbons. Here we will see plus I effect with the, what do you call as here, 3 carbons on this carbon here. This is going to have plus I effect, hyperconjugative effect, and also hyperconjugative. 6 hyperconjugative structures, and these 2 methyls plus I effect, and this also causes, propyl is also causes plus I effect. See here, only plus I effect. You can't see hyperconjugative effect on this carbon here, right? Here you can see plus I effect both ethyl groups and hyperconjugative effect. But here, what I'd like to show you people here, one of the important aspect that I'd like to bring to your notice. See, the order of effects, plus M is greater than, plus hyperconjugate effect, and plus I. See, where the many effects are present. See, it's having plus I, but here it's having plus I and 6 hyperconjugative structures. That's why this is giving more stable carbocation and undergoes fastest dehydration. When it undergoes fastest dehydration, it gives Sedzef's product also, Hoffman's product also. That depends upon what do you call as here bulkiness of the alkoxide, right? So this is what's called here one of the most important aspect, because in the second compound it's going to have plus I more hyperconjugative effects due to 2-methyl groups. That's why it undergoes fastest rate of dehydration. Let me do this also, children. Consider the following. What's called here? Consider the following reaction. Very simplest reactions, children. Cyclobutyl methanol. That's going to have this. Here CH2OH. CH2 group is out of the ring nana here in presence of acid. And what's called here, that's they have given in presence of acid. A is the major product. That's the question. What's the major product? They should write here. We should write major product, right? When we have written as major product, then what's going to be happening means that's major product is that when there is OH, CH2OH means OH is out of the ring, then it undergoes ring expansion to get the stable ring due to reduce what do you call as here angle strain here. CH2OH, this forms carbocation. And this bond, what do you call as water is eliminated. OH, H plus water is eliminated. That's going to be CH plus, gives rise to the compound is going to be this one. And this is the plus. And whereas this one is going to be shifted here and minus H plus gives rise to the compound. It's what's called here. That's nothing but the major product is going to be this here. When you got this and this is shifted here, this is going to be happening with respect to this, right? It's clear. Whatever is called here, that's we are getting. What's the product you are getting here means that's nothing but the C1, C is going to be the product here. This is shifted here. This acquires positive charge here. That's why it's what we are not this. It's a little error is there. That's we will do because this is what you are going to get. This part is concerned. Let's do this. So children, and now this is shifted here. Here you are going to get the positive charge. This is going to be the positive charge with respect to this. And that is going to be positive charge, right? It's what's called here CH2 plus. This what we are going to see, the CH2. That's the compound you are going to get, CH2 plus. This is an alkene which you got here. Clear? This is the cyclopentane. It's clear. 8. One is also finished, children. Let's do it. Whenever you are going through this, and we have to go the next step of the reaction, next question of this reaction. And whenever you are going to this next question of this, see, listen, very simple. The main product upon what you call as here CH3, CH2, Br and AgCN is. Then we will do this also, children. Whenever that's called here ethyl bromide is reacted with. Actually, this is a SN2 reaction based on the solvent AgCN. This is what's called here plus pseudo-inert configuration, more covalent nature. Nitrogen is more electronegative. Hence, this won't liberate carbon cyanide so easily. That's why this lone pair will attack here and eliminating this one. and giving us the isocyanide, the ethyl isocyanide, the ethyl isocyanide. That's the product which we are going to get here. Suppose if you are taken what you call as here alcoholic KCl, alcoholic KCl means that's going to be the alcoholic aqueous KCl, K plus Cl minus you are getting. So that's why what you are going to get means ethyl cyanide is the major product. So that's the question here with respect to this, the main product. This is an SN2 mechanism, children. It's simple. What's that reaction means? It's diazotization followed by diazotization. Its aniline is subjected to diazotization. It's cuprous halide in presence of HX. That's going to be known as here Sand-Meyer's reaction here. So that's what we have seen in the given one is Sand-Meyer's reaction. But here you can't prepare by this way iodobenzene. Chlorobenzene and bromobenzene is possible. Iodobenzene means you have to take Ki here. Then next, the product of reaction with alcoholic silver nitrate and ethyl bromide. It's really, really important, children. We will do this also. What's the way to do this means? Alcoholic silver nitrite. Let's do this. Whenever you have taken alcoholic silver nitrate with ethyl bromide, that is going to be AgNO2. It depends upon solvent, but in this case, though it is going to be covalent, what's happening means nitrogen is going to be attacking this one and gives rise to nitroethane as the major product. Nitroethane as the major product in presence of alcohol, and ethyl nitrite is going to be the minor product. Ethyl nitrite is going to be the minor product. Ethyl nitrite is going to be the minor product. Right? Then next, that's what we have seen with respect to this. And whenever we are going to see, this is the options which they have given, but major is going to be this, what's called here nitroethane is going to be the major product, follows SN2 mechanism. And this is the carbon halogen bond is strongest among the following. So that is going to be strength of the bond, whatever is called here strength of the bond. As far as strength of the bond is concerned, it's directly proportional to electronegativity. And strength of the bond is directly proportional to bond order. Strength of the bond is going to be inversely proportional to bond length. So that's what we are going to see the concept with respect to this, right? So like this, what we are doing is nothing but all these questions here. And of course, children, be cautious. Every hint is given in our book also. It's a very simple possible question which you can do over here. The strength of the bond is directly proportional to electronegativity. That is, fluorine is most electronegative. Hence, that's why it's going to be the strongest bond. Whose bond length is more means Ci bond length is going to be more and than CBr, than CCl, and what's called than CF. That depends upon bond order as well as electronegativity also. That's possibility is there. So the bond length is concerned. Ci is greater than, CBr is greater than, CCl is greater than what's called CF. And whereas strongest strength of bond is concerned, CF is greater than, CCl is greater than, CBr is greater than this. It's what we have done.